So we are going to start looking at section 5.3 today. I don't think we'll get this finished, but that's fine. We're going to look at the fundamental theorem of calculus part 2. On Friday, we spent all our time just finding antiderivatives so that we'd be up to speed in order to do this. So let me show you what the fundamental theorem of calculus says. And it's quite, in my opinion anyway, it's quite amazing what it says. It's all about finding the exact value for an area under the curve. So I want you to imagine that we had a curve, just like the one I'm trying to draw here, starting at x equals a and finishing at x equals b. And we want to find the area, technically I should call it the net area under a curve. And we did some split it into strips and Simpson's rule and all sorts of other stuff. We did one really horrible example of making the limits go finite. But the area under the curve from a to b of this function with respect to x is simply just capital F of b take away capital F of a, where capital X, f of x, is the antiderivative of f of x. So I'm now going to just start off nice and simple ones. I'm now going to show you how you apply that. Suppose you had the function x squared and you want to find its area between 0 and 2. So I can imagine it might look something like this. And you want to find the exact area under the curve. Well, the integral from 0 to 2 of x squared, because that's what f of x is the antiderivative evaluated at the end, take away the antiderivative evaluated at the beginning. And we set out the working in a very specific way, which you'll probably find almost every textbook does the same. What is the antiderivative of x squared? Remember the power rule from Friday. The antiderivative of x squared.
1/3 x cubed.
Right, add 1 to power, divide by the new power. And then you do a funny little vertical line and you write x equals 0 to x equals 2. And that's just how we write down antiderivative evaluated at here and here. And then you simply just plug into, take away, plug in 0, and the answer is 8/3. We have just found the exact area under that curve. Right, so it's not an estimate, that's the perfect answer, and it's 8/3, and I did it in about a minute. Right, if you wanted to do that using, say, TA or SA, wouldn't that only give me an estimate, and wouldn't that take me forever and a day? Now, isn't that a cool algebra way of solving that problem? Right, let's do another one, make it harder. I'd like to get the area from 1 to 3 of 8x cubed plus 4x plus 1 dx. Well, power rule, add 1 to the power and divide by the new power. Add 1 to the power, divide by the new power, and the number 1 gets you x, and you evaluate it at 1 to 3. If you plug in 3, you get 2 lots of 3 to the power of 4, add 2 lots of 3 squared, add a 3. So that's basically that's basically the antiderivative at 3. Take away the antiderivative at 1, so 2 lots of 1 to the 4 plus 2 lots of 1 squared plus 1. That's essentially the antiderivative at 1 then. And what do you get? 81, 18, and 3. Take away 2, add 2, add 1. So basically take away 5. That's 99, 102, take away 5. I believe the answer is 97. I've just had someone come in and I've got a little window open somewhere. There we go. Are you comfortable with the process of finding the area under a curve? Is basically finding the antiderivative and evaluating it at the big number, take away the little number. And the area of that particular curve, which I don't even need to draw to get the answer, would be an exact value of 97. Okay. Let's put in the integral from 1 to 2 of, what shall we do this time, of e to the x. Oh, let's make it 2, 2e to the x. Antiderivative of 2e to the x. Friday's work. Antiderivative of 2e to the x.
2e to the x.
Okay. And then we're going to evaluate that at x equals 1 to x equals 2. Now, in these questions, we want exact answers. So you plug in 2, you get that. You plug in 1, you get that. That's basically the answer. Right, I don't go and figure out that that's 12.1234566. I don't convert it to a decimal. So it's okay to have root 7 plus 3 as an answer. It's okay to have 2e squared minus 2e, you know, as an answer. In fact, that's the answers that we want. Do a trig guy. I want to do the integral from 0 to pi upon 4 of 2 lots of sin x. So we need to do an antiderivative of a sine function, and then we'll evaluate it at 0 and pi upon 4. Okay, be careful about the sign. What is the antiderivative of 2 sin x?
Is it negative 2 cosine x?
It is. Now, if you plug in pi upon 4, you get negative the cosine of pi upon 4. Take away negative the cosine of 0. And this means that you have to go back to your 152 world, because I do not want to know that that is 0.707, which is what it is as a decimal. We need trig questions to be exact values. That means you're going to have to go looking for the sine 2/3 pi and the cosine 5/4 pi and things like that, right? So you have to, if you've got your unit circle handy or whatever it is, shake the dust off it and bring it out in front of you because you're going to use it. What is the exact value for the cosine of pi over 4?
Is it the square root of 2 over 2?
It is. Take away means add. What's the cosine of 0?
One.
So add 2 lots of 1, add 2. I would probably tidy this answer up a little bit. I think 2 belongs in the front and don't these cancel. So I would have eventually written that down. Are you comfortable about switching orders and cancelling some 2s? You see what I did there? Cancelled those 2s to get this guy. And I think it, to me, maybe I'm just awkward, but that looks clunky. Doesn't that just look nicer? I think it does anyway. I'm pretty sure WebAssign would take both those answers. I'm pretty sure it will not take that as the correct answer because that's not, there isn't style points, right? You haven't made it as pretty as it could. Any questions so far? Are we quite comfortable with how to find the exact area under a curve now? Agreed? So I'm going to show you a weird answer. It's correct, but it's weird. Can you pretend that we're going to do the area under the curve from 0 to 2 pi? That's a bit messy. That says 2 pi, right? Well, it's going to be the integral from 0 to 2 pi of sine x dx. The integral of a sine, we already did that, so it's negative cosine, evaluated at 0 and evaluated at 2 pi. So that's going to get me negative the cosine of 2 pi, take away negative the cosine of 0. Isn't the cosine of 2 pi 1? So this will be negative 1. Isn't the cosine of 0 also 1? So won't this be plus 1? And the weird answer is 0. And if you look at my very, very badly drawn picture, can you imagine that that guy and that guy are equal in size, but this guy is a positive and this is a negative? And since they're both the same, can you see how when you do a net area, they essentially cancel each other out and the net area becomes 0? Show you what this piece is, 0 to pi. Well, it's negative the cosine of pi, take away negative the cosine of 0. Okay, cosine of pi. What's the number?
-1.
Oh, sorry. I'm saying -1. Or is it 0? Now, if you look at the cosine function, it's -1, isn't it? And what's the cosine of 0? Oh, sorry. There it is, that's better. What's the cosine of 0?
1.
1. Take away -1 is add 1. 1 add 1 is 2. That guy up there has an area of 2. Isn't that surprise? To me, isn't it surprising how nice a number that is? You would think something underneath a curve like that would be some weird fraction or something. Oh, and I can tell you what that one is. Do you know that's going to be -2 if you just did dairy there? Can you see that the 2 and the -2 cancel out? So the fundamental theorem of calculus allows us to find the area under a curve, the net area under a curve, by simply just getting the antiderivative and evaluating at the end, take away the beginning. So let me find some questions where we get to do that. This is similar to question 4. Okay, back to Friday again. I know I'm going to have to find the antiderivative of the square root of x. Why am I converting the square root of x into a half power? What was my motivation for doing
Makes it
that?
easier to use the power rule.
Okay, agreed. And the power rule is add 1 to the power, divide by the new power, and that's going to get evaluated at x equals 1 and x equals 9. And then I'm going to use style points. This guy is easier to get an exact value from. If you start plugging 9 in here, aren't you going to have 2/3 9 to the 3/2? And you know that's not considered style points a good answer. Right? So returning back into square roots, it's 2/3 the square root of 9 cubed, take away 2/3 the square root of 1 cubed, which is basically 1. That guy gets you 2/3 9 root 9. This guy gets you 2/3. Oh, by the way, that's 3, so that's 27. That cancels. You get 18. Eventually, you get 18. Take away 2/3. And that's 54, so 52/3. You can fill in the details yourself. I zoomed through that, but I think I'm right. Oh, in case you're wondering what I was doing there, isn't the square root of 9 cubed the same thing as the square root of 9 squared times another 9? And isn't the square root of 9 squared just 9? And isn't the square root of 9, 3? And that's where the 27 came from. And 2/3 of 27 are 18. Now, why is that helpful? Well, suppose the number wasn't pretty. Suppose it wasn't 9, suppose it was 7. Then I would convert that into that. You see, it can be turned into a relatively nice looking exact value. So that was a little piece of algebra I did there. This technique of converting it to fractional power is the same thing you're going to do when it's 4 times the square root of x or 3 times the cube root of x. You know, anything with squares and cube roots in it, right? Let's do another square root, cube root kind of guy. Let's do the integral from 1 to 8 of 4 over the cube root of x. Now you're going to have to think a little bit harder about this one now. I do not want a cube root of x. I need a fractional power of x, don't I? So I need some conversions. What does this become as a fractional power of x?
X to the 1/3.
Negative 1/3?
Well, we have a choice. I hear negative 1/3 and I hear 1/3. You might be just looking at the bottom and saying 4 over x to the 3rd. And if that's all you meant, that's fine. But can you see that because it's on the bottom, it's a negative power? Now, what we're going to do now is antiderivative using power rule. If you add 1 to that, you get 2/3. Dividing by 2/3 is the same as multiplying by 3/2. 3/2 times this guy gets me 6. Are we, well, why did I put that funny 8 there? That's better. From x equals 1 to x equals 8. That's going to be the cube root of x squared. And do you see I'm doing my little style point thing? Although I needed fractional powers to get the antiderivative, when I come to evaluate the thing, it's much better if it returns to its cube root form. Now, in this case, it's going to be 6 times the cube root of 8 squared, take away 6 times the cube root of 1 squared. 8 squared is 64. Square root of 64 is going to get me what? 2. No, it's 248. Can't do it in my head. Okay, square root of 64 is, now I can do it in my head. Cube root is 64. It's a nice number. Oh, come on, cheer me up.
Is it 4?
Cube root is 64. Yay. I believe the answer is 18. Now, if it didn't come out right, it's okay for the answer to be 6 cube root of 17, take away 4 or whatever, right? It's still an exact answer. If it's nice, you should make it nice. If it doesn't work, then whatever you've got is the answer. That's what you've got. Are we doing good? Right. This one is similar to question 6. I don't think we've done one quite like this on Friday. So it's not really ready to be turned into an antiderivative yet, right? There's a square root floating about, and it's what, a square root times something. That's not good either. What do you think I'm going to do with the square root of t as a kind of starting point to this process? What do you think I'm going to do?
Change the square root of t into t to the 1/2.
Have you noticed that that's a good starting point, even if you don't know what to do next? I mean, just do that while you're thinking about the question, right? So you do that and then you look at it. And then maybe the next step will come to you. I've got this, which is totally useless for the power rule. I mean, isn't the power rule t cubes and t to the halves, right? It's not this times that, right? We never use a power rule with a this times that. So what do you think I might be doing next?
You can multiply out.
Okay, and that times that gets me 3t to the half. Take away. Now be careful here, I guess I'll do it in a little bubble. If you take a t and you multiply it by t to the power of half, don't you get t to the 1/2, which we call 3/2? Are you comfortable with that little thing? And it's a minus. Now, although that might not look pretty, isn't that at least doable now using the power rule? Agreed? It is doable now. So we will add 1 to the power. If you divide, dividing by 3/2 is the same thing as multiplying by 2/3. Can you trust me that if you multiply by 2/3, that becomes 2, right? 3 times 2/3 gets you 2. In this case, you add 1 to the power and you divide by the new power. You get that. Then you evaluate it at 0 and at 9. And I'm going to do my typical that guy. Not as pretty as I'd like it to be, but I'm going to get a 9 cubed here. I'm going to get a 9 to the 5 here. The only good news is, isn't the second term just 0? plug in 0 here and plug in 0 here. It's not that uncommon when you do these questions for typically the second one to be 0. If you know it's going to be 0, I wouldn't even bother writing 2/3 the square root of 0 cubed, take away 2/5 the square root of 0 to the 5. If you know the whole mess is going to be 0, just say minus 0 and save yourself some work. Now, this guy can be simplified a lot, and this guy can be simplified a lot. And they actually come out as nice numbers. This one becomes 3 cubed, which is what? 3 cubed is 27. And this one becomes 3 to the power of 5, 3, 9, 27, 81, 243. 2 times 243 is 486 over 5. And 54, if you turn it into fifths, 54 is 250, 260. Take away that guy. And that's negative 226 fifths. Don't quote me in that because I'm doing it all in my head. Let me show you a little trick. I could find 9 cubed and then get the square root of it. And you're going to have to trust me that it's 27. Or I can do this. Isn't the square root of 9 cubed the same thing as the square root of 9 cubed? In other words, switch the order you do the thing. Now, the square root of 9 I can do in my head. Isn't that 3? And 3 cubed is 27. So that's where that 27 came from. Right, that one there. Now, let's look at this fella. Couldn't we do this fella by finding the square root of 9 to the power of 5? In other words, switch the order. Now, why is that easier? Isn't it easier to find square roots and then power them up than to power them up and then try and do a really, really big square root, right? Just the order tends to work better. Now, the square root of 9 is 3, and 3 to the power of 5 better be the number I think it is. So here goes. 3, 9, 27, 81, 243, double 243 is where that came from. So you're wondering where these came from. This is what I was doing in my head. Are we okay with that kind of shortcut for ugly square roots, cube roots kind of thing? You can do both. Are we good? Now, there is a huge, huge number of different versions of this question. So here's another one. You got to treat each one as an individual because it's not one method works for everything. I got to figure out how to deal with this guy algebraically. He is eventually going to be kind of partly a power rule. But right now, he is no good to nobody, right? Any suggestions for a better way to write this down that might help us to use the power rule?
X squared plus 4 times x to the negative 1.
Nothing wrong with that. That works totally fine. If we go this pathway, x to the negative 1 times x squared gets me x. And this second guy is correct, but I'm not going to use him. Not in that form. Now I'm going to use him. Why does that guy is okay to use the power rule, but this guy isn't? this guy has to be written in a totally different way, because isn't he a special case? Power rule doesn't work with -1. Think of the rule, add 1 to 0. Divide by the new 0. Do you see? Yeah, danger, Will Robinson, right? 4 over 0 is not a good thing to deal with. So now we can do the antiderivative. Power rule works fine with this one. Add 1 to the power and divide by the new power. What is the antiderivative of 4 over x?
4 tan x.
Not
Or,
tan,
no,
but it is.
not tan, natural log.
Agreed. Are we cool on that one? Now, let's plug in the numbers. 1/2 times 2 squared plus 4 times the natural log of 2. Take away 1/2 times 1 squared, add 4 times the natural log of 1. 2 squared is 4, half of it gets you 2. And I'm just going to leave this guy as 4 log 2. 1/2 times 1 squared is still 1/2, so I'll take away 1/2. What number is the natural log of 1?
0.
So won't that just basically be 0, so I'm not going to write it. It's gone, it's 0. Now, this guy and this guy, when you combine them, are 1 1/2, but we never write 1 1/2, don't we? Write 3 over 2, improper fraction, which is what 1 1/2 looks like. And this fella here, right now, is going to be written like that. And I don't know if WebAssign will take that. It might not. I do know what it should take. And you might think, oi, where did that 16 come from? Isn't 4 log 2 the same thing as the natural log of 2 to the power of 4? 2 logs added, you multiply. 2 logs subtracted, you divide. If you multiply a log by a number, doesn't it become a power? That's the third law of logs. Multiply by a number, that number becomes a power. And that's 16. So that is guaranteed to be correct. That may or may not be accepted in WebAssign. It's a lucky dip. Sometimes they do it and sometimes they don't. Are we good? No one's noticed something that I haven't done, yet on Friday I did. In every question on Friday, although a couple of the times I forgot and had to go back and do it, what else do you do when you do an antiderivative?
Add the arbitrary constant.
Right. Have you noticed that I didn't bother writing any arbitrary constants here? And the good news is it's not a mistake. I'm not going to go back and put them all in. The answer is you don't need them. And you might say, well, why don't I need them? Well, technically speaking, let's do this one. If there was an arbitrary constant C, right, wouldn't each one have a C in it? And wouldn't the first plus C get subtracted by the other plus C? Don't the arbitrary constants kill each other off every single time? And since we know that that's going to happen, why bother writing something in if you know it's going to disappear? So it's a bit of a mathematical convenience to not write plus C. If you want to be lawyer-esque about it, it is there, but we just don't write it. Right. So it is got antiderivative plus C, then we plug in the numbers, but the first plus C, take away the other plus C, they always disappear, so it's never going to be in the final answer, right? It's never going to exist. So that's the way everyone does it in math. When you do antiderivatives and you're using them for areas under curves. You do not do the plus C.
Sorry,
You
Professor
don't.
Robertson, I might be a little OCD, but
Yeah.
on the last problem you did, was there supposed to be a plus sign on the 3/2 natural log of 16? No, it was the other sheet, the most recent sheet.
This one here?
Right, where you circled the answer at the end. Should there be a plus sign there, or did I just miss that?
No, you are right. I missed the plus sign.
Okay, okay. I saw it
There
there. I
should
was
have
like,
been
I
a
might
plus
miss
sign
something,
there,
but
and
okay.
you didn't miss something. I missed something. You got it right. Whew. That's it. I'm taking 10 points off you, Hector, because you went and caught me in a mistake, and I hate people catching me in mistakes. No, I don't. I really like it when people catch that, because it tells me that you've been paying attention, number one, and doesn't it kind of convince me that you know what the heck I'm doing, right? And so that is good news. I want everybody to do what he did. If ever I screw up and I write down 2 times 3 is 9, your job is to tell me that it isn't, it's 6. If I do a plus where a negative should go, or I miss a plus out, you will tell me. Because aren't some of you going to look back at your notes and think, how come that turned into 3/2 log 16? Is that something to do with logs that I've forgotten? And you'll throw yourself totally off track when the answer was, I just forgot to put a plus in, right? Which is much easier to live with. Now, occasionally, because it happens, you're going to point out something and say, I think you made a mistake there. And I didn't. And that's totally fine, because that's going to happen. But 9 times out of 10, I'm the guy who made the mistake, and you're telling me something that needs fixing. And I'm okay with occasionally, I think that should have been 3/2, not 5/2 or whatever. And then I'll check it through and say, nope, it's 5/2 and we're good. And that's fine. I like that. So I'm giving you your 10 points back, Hector. Right, which is kind of what the plus C does. Don't you give it, then you take it away. Right, so there's an analogy for you. It's in my head, and hopefully you'll just get used to the way my brain works. When something comes into my head, sometimes I have to just tell you to get it out the way so I can focus. You know, you had a question where you had that calculation. And I said, look, you have to call it 1.5, but you have to call it 3/2. And fractions, when they are written in this format, are called improper fractions. Which, God, I don't know how far back that goes, right? You were 7 or something when you found out about them, right? Or 10 or whatever age you got those. Improper fractions is the name to that, but that is not the name that I use back home in Scotland. And I believe they use it in Britain, but I know for sure they use it in Scotland. I like names of things that give you an idea of what it is. To me, improper fraction is an ugly label or name, because in a way it sounds like that's the wrong way to write it, right? It's improper, but that's the way I want you to write it. Actually, if anything, I would call that a proper fraction if I had to give it a name. But we have a much better name in Scotland. Look it up. It's called a top-heavy fraction. I like that name. Doesn't it give you a kind of idea of what the thing looks like? It's big on the top, it's top-heavy. See how names can help you in your understanding and other names don't help at all? And occasionally, sometimes names give you the wrong idea, right? Like improper fraction. Sounds like it's wrong, right? It's improper, but it's not. I think top-heavy is cool. Have you noticed I also make up names for things like, as long as you do it to both sides, it's okay rule? Have you heard me say that yet? Right. Now, that isn't on the internet, but I like names that tell you what you're doing. right? And so I think that name, as long as you do it to both sides, it's OK rule, is quite a good name for the process, isn't it? That's how you solve equations and things. Are we good? Ready to move on now? How about this one? It's like question 7. It's not quite question 7, but it's like it. Well, let's do the good news first. You do not need to algebraically change it, fix it, rearrange it, or anything. It's good as it is. The 2 is not a big deal. What is the antiderivative of 1 over 1 plus x squared? And we did that on Friday. 1 over 1 plus x squared. Or if you like, 1 over x squared plus 1, which is the same thing. It has an antiderivative.
Arctan of x.
And I'll call it inverse tan. The arctan is another name for it. And now we're going to hit the problem. That is not the final answer. We have to find exact values for the inverse tan of root 3 and the inverse tan of 1. And if you think back to finding exact values for sines and cosines, at least your unit circle can help you, right? You can look up pi upon 6 and find out what the exact value of the sine and cosine is. You're going to have a real problem trying to do inverse, but nonetheless, we need to know who it is. So here goes. I'll do it over here. This is a trick that you may have seen before. You have to memorize 2 triangles to do this. These triangles that I'm about to show you will allow you to get exact values of sines and cosines and tangents, and indirectly will allow you to find inverse sine, inverse cosine, and inverse tangent. And the triangles are 1, 1, root 2. That's the first triangle, and that's the triangle that you're going to use when the angles involve pi upon 4. Has anybody seen that triangle before? Now, the second triangle is going to be for the pi upon 3 and the pi upon 6, guys. And for those triangles, 2's going to go there. Well, let's do it in order. 1, 2, root 3. So 1, 1, root 2, 1, 2, root 3. Now, if I have these triangles and a bit of paper somewhere at my side, I can use these to get exact values of sines and cosines and tangents. So let me use it for that, and then I'll show you how you can use it for inverse tans. Suppose I wanted to find the exact value for the sine of pi over 6. Now on my triangle, pi upon 6 is here. Great. Can you remember from SOHCAHTOA what the combination for a sine was?
Opposite over
SOHCAHTOA.
hypotenuse.
Now, from this angle's perspective, isn't the opposite 1 and the hypotenuse is 2, right? From this angle's perspective, this side is called the opposite and that one's 2. So that tells me the answer to this is a half. Suppose I want the tangent of pi upon 4. Then I go over here. According to SOHCAHTOA, what is the formula for getting a tangent?
Opposite over adjacent.
Now, from this angle here where my finger is, isn't the opposite 1 and the adjacent is also 1? And so the tangent of pi upon 4 is 1. So far, so good? Right, now, if you wanted to get the tan of pi upon 6 or the cosine of pi upon 4 or the sine of pi upon 3, wouldn't it be one or other of these triangles and a little bit of SOHCAHTOA? So do you see that these contain all the base angles, right? Pi upon 3, pi upon 4, pi upon 6. And can't you use them to get all your sines, cosines, and tangents? Great. Now, I would like to use these triangles to answer what angle has an inverse tangent of 1. Oh, wait a minute. I think I've got it in front of me, don't I? What angle has a tangent of 1? Pi upon 4 has a tangent of 1. Okay, now a sneakier one. I need an angle whose tangent is √3. Now, looking at these two triangles, which one of these two triangles do you think has got a fighting chance of giving you √3? First triangle or the second?
The second triangle.
Because it's the only one that's got √3 in it, right? That's check off 1. Now, from this angle's perspective, is the tan of pi upon 3 √3 or the tangent of pi upon 6 √3? Because you just need to check two tangents, right? So is the tangent of pi upon 3 or is it the tangent of pi upon 6? Well, let's look at the tangent of pi upon 3. Opposite over adjacent. Oh, got it the first time. So this guy, right, is pi upon 3. Couldn't I also use this triangle to get inverse sines of a half, inverse sines of 1 over √2, inverse sine of √3 over 2, inverse cosines, and so on? So that's just another way of you tackling the question that we've now returned to back here. The inverse tan of √3 is this guy. So 2 times pi upon 3. And the inverse tan of this guy is pi over 4. So what am I looking at? I'm looking at 2/3 pi, take away 1/2 pi. Do you think that's the final answer, or do you think there's some style points left?
I think you can simplify it more.
Yeah. Don't you basically have to just add 2/3 and take 2/3 and subtract a half from it? Now, if I was going to do that, I would convert this guy into 6 and this guy into 6. And that gives me the ultimate final answer, which is 1/6 pi. Does that look good? Right. Okay, it's time. So say hi and bye-bye.